Alright, here we will learn about a new topic, that is phasor diagram. So we have seen in the previous videos of this chapter that both alternating current and alternating EMF varies sinusoidally with time. Okay, so when the EMF and the current are having no phase difference, okay, so when the phase difference between the current and the EMF is zero, okay, so for the phase difference we denote by phi. So when the phase difference is zero, then it means both will reach zero maximum at the same time. Okay, so when the current is here, the voltage is here. When the current is maximum, the voltage also will be maximum. So in this way, so this is the case when the phase difference between the two waves is zero. So please note down here that this solid wave stands for the EMF and this dotted wave stands for the current. Okay. Now, to represent the wave graphically, when the two waves are out of phase, then it becomes a little bit complicated. So in such case, what we do is we use a new concept to represent the wave, to represent the two waves when they are having some phase difference between them. And that new concept here is phasor diagram. Okay. So in phasor diagram, what we do is we represent the two wave, like the two currents and the EMF as a rotating vectors which rotate with some angular speed and having some phase difference between the two. Suppose this is my coordinate axis, in which this is the x-axis and this is the y-axis, and say this is the origin. Alright. Now if you represent the alternating EMF using this phasor diagram, then I will write, I will draw a line or say a vector, and this vector here means is E0 for the EMF. The magnitude of this vector means the maximum value. Similarly, when you represent the alternating current using this phasor diagram, then the magnitude of that vector should be the maximum value of current, and that will be I0. Okay. So we know that the value of the EMF at any instance of time is given to us E equal E0 sine omega t, where E0 here stands for what? The angular frequency of the alternating EMF, and E0 stands for the maximum value of the alternating EMF. Alright. Now, let's say this vector E0, it is rotating in the anti-clockwise direction with some velocity, and that velocity here is the angular velocity, which we denote by omega. So this angular velocity is the same as angular frequency in this case. Alright. Okay. When it rotates, then we can say the angular velocity is omega. Suppose at any instance of time, let's say this E0, it makes an angle omega t with respect to this reference line xx dash. Okay. Then what will happen when this E0 is parallel to when this E0, let's say it starts from this reference line, and if it is being parallel to the reference line, then the angle omega t will be 0. So when omega t is 0, then in this equation I will have, when omega t is equals to 0 degree, then the value of the EMF E equal sine omega t means sine 0. So sine 0 is 0, 0 into E0 will be E0. It will be 0, I mean. Okay, which means when this angle, right, when this vector, it is parallel to the x-axis, we have no EMF. So in the graph, That means this is the point when the angle omega t is 0. Alright. So as this vector E naught rotates, let's say till this position, then how much is the angle of omega t in this case? It will be pi by 2. So when omega t is equals to pi by 2, we have E is equals to how much? E naught sine pi by 2. You know sine pi by 2 is equals to what? So 1 times E naught will be E naught. Okay. So if you represent this point right in the graph, you will get this is the point, which is the maximum value of alternating EMF. And this point, it corresponds to the angle pi by 2. So similarly, right, when this vector rotates till this position, then this angle omega t will be how much? Will be equals to pi. And if omega t is equals to pi, then E will be equals to E naught sine pi. You know sine pi is 0. 0 times E naught will be 0. So in the graph, that means this is the point. Okay. Next, again, as this vector rotate, suppose now it is lying at this point, at this position, then this angle right from here to here will be how much? Is equals to 3 pi upon 2, or I can say 270 degree. So if you substitute omega t equal 3 pi upon 2, then you'll get E equal how much? E equal, because sine 3 pi by 2 is minus 1, so minus 1 times E naught will be minus E naught. So again, right, at this angle, the EMF is maximum, but in the negative direction. So in the graph, that would mean this point. Okay. So again, if I rotate this vector like this from here to here, right, I mean the whole angle in this case will be how much? Whole angle will be 2 pi. So if the angle is 2 pi, then how much is E? E equal E naught sine 2 pi, and sine 2 pi is 0. 0 times E naught will be 0. And in the graph, that would mean this point. Okay. So in this way, right, you'll get 0 maximum, 0 maximum, 0 maximum, okay, at different values of angles. Okay. All right. Also, if you remember, in geometry, we have these are the quadrants. Okay. This region here is known as first quadrant. This is second. This is third. This is fourth. So if I rotate a vector from here to here, that means you are completing the first quadrant. So that first quadrant in the graph, it means a curve from this point O till this maximum. And if you go like this, in the second quadrant, it means from this point to this point. In the third quadrant, it means from here to here. In the fourth quadrant, from this point to this point. Okay. All right. So now, as I already mentioned before, that in this chapter we are having two sinusoidal waves. One is the EMF, another is the current. So how do we represent these two waves using a phasor diagram? Okay. Now, if the two waves they are in phase, if the two waves are in phase, then the equations of the two will be E equal E naught sine omega t and I equal I naught sine omega t. So in this case, the phase difference is equals to 0. So when the phase difference is 0, it means if this vector E naught is pointing in this direction, then my vector I naught also will be pointing in this direction. So this is the phasor diagram for 0 phase difference between the two waves. Alright, next, if I say that the current leads the EMF, suppose I leads the EMF by an angle phi, which means if this is my vector I naught, this is my vector E naught. So the difference between the two is phi. And this angle in which this E naught makes with the horizontal line or reference line, it is omega t. So when the current leads the EMF, it means the current is going fast than the E naught. So in that case, the equations of the EMF will be E equal E naught sine omega t, and I will be equals to I naught sine omega t plus phi. Alright, next, if the current is lagging behind the EMF, okay, so this is my reference axis. The angle that E naught makes with the reference is always omega t, okay, and if this angle here, let's say it is phi, then I can see here, because E naught is above, I naught is below, it means the current is I is lacking, okay, or I can say I is lacking behind E by an angle phi. Okay, so if the current is lagging behind the EMF by an angle phi, then the equations of the instantaneous EMF and current will be E equal E naught sine omega t, and I will be equals to I naught sine omega t minus phi. Okay, I hope this is clear, because looking at this equation, at this figure, omega t is the angle between E naught and the reference. Okay, so now what will be this angle? This angle will be omega t minus angle phi. Okay, so these are the three cases about to represent them in a phasor diagram. So in the next video, okay, we shall see about how to represent a phasor diagram for a circuit containing only a resistor, a circuit containing inductor, and a circuit containing capacitor, and so on. So that we shall do in the next video.